Good morning, one and all. Today I am discussing about fluid mechanics and hydraulic machinery laboratory for 18CVL48 for course semester students for calibration of Orifice meter. So the content is to determine the coefficient of contraction and coefficient of discharge for a sharp-edged Orifice discharge. Apparatus are constant at water supply, sharp-edged circular orifice, hook gauge, micrometer, contact gauge, measuring tank, stopwatch. An orifice is an opening in the side wall of a tank and the liquid flows out of the tank when the orifice is open. In a sharp-edged orifice, there is a line of contact of liquid, it flows out. An orifice is called as an orifice discharging free when it discharges into an atmosphere a jet coming from the tank from an vena contacta at a distance d by 2, where d is the diameter of the orifice. The orifice are commonly used for determining the discharge. You can see here in this case, this is in an orifice. In a local language, a tank with a hole, how the water ejects, that itself can compare with an orifice. So now the calculation part, the number one is we have to calculate what is called as the coefficient of discharge. Coefficient of discharge is given by formula Q actual divided by Q theoretical. Q actual is equal to AH by T, where A is the area of the collecting tank in meter square, H is the rise of water level out of collecting tank, and T is the time for H rise in water level. Theoretical discharge, Q theoretical is equal to A into root of 2GH. So where that is G is acceleration due to gravity, H is the head above the orifice in meter, so meter, and A is cross section area of the jet. So here we can see here, this is your collecting tank, area of the collecting tank, height, rise in the height at a time interval will give the Q actual, whereas Q theoretical is given by A into root of 2GH, where A is nothing but cross sectional area of the jet, so that is your orifice, pi d square by 4. H is the head of water above the orifice up to here. So by substituting we will get CD. Then coefficient of velocity CV is equal to root of x square divided by 4yh, where H is H1 difference, H2 head, initial head, final head. X is x dash minus x naught will be x. Y is y dash minus y naught will be y. The procedure part, coming to the procedure part, first measure the diameter of the orifice. From that calculate the area of the orifice, pi d square by 4. Next is 4 trials we have to do it by adjusting the inlet valve. One is opening the inlet valve to 25%. Calculate what is the time required to collect the water in the collecting tank through the orifice. Thereby you can calculate discharge, and from the nappy how much the jet of water eject, this horizontal vertical distance you have to calculate. Okay, so for one valve opening for 25% opening or 50% opening or 75% opening or 100% opening, this all we have to do it. Only thing is the ejecting jet length depth by using gauge we have to measure at which what depth it touches the surface of the water. That is point number 1. Point number 2, in a collecting tank, for a specified time interval, how much volume of water will be collected. If you know these two parameters, by using the formula we can calculate the rest of the thing. That's all the procedure part. Let us not have too much debate on the procedure. Okay. So this is simple procedure part I am explaining to you. Coming to the observation, the diameter of the orifice is 1.10 to the power of -2 meter. Area of the orifice is pi d square by 4 into h. Length of the tank 40 into 10 to the power of minus 2 meter. Width of the tank 45 into 10 to the power of minus 2 meter. Area is L into B, that is A is equal to 0.182 meter square. The coordinate of vena contact is x naught, y naught. What is x naught, y naught? You can see here. X naught is from the edge of this tank to here is x naught. From here to here is the scale height is y naught. Prepare a table composed of trial number, head of water. Head of water means this height. It should be kept constant before starting the experiment. Initial level reading H1, final level reading H2, and rise in the water head H, that is in your tank H1, H2, H. Next, time taken, time interval, Q actual, x dash, y dash, total distance from the edge of the tank. So x is the x dash minus x naught as I explained earlier, y is the y dash minus y naught, CV is exponent by 4yh, Q theoretical, Q actual is one, calculate CD. Okay, so what we have to do here is, first trial 25% valve opening we have to do it and ensure that water will remain standby. Then open the orifice mouth here, then the flow of water takes place. The flow of water from the outlet of the tank, that is at the orifice to your tank distance, you measure it x naught. From the scale, the depth you measure it, the top of the orifice is y naught. Afterwards, this jet of water will somewhere touches the collecting tank surface. Move the gauge so that it should not touch the water, it touches, splitting of water takes place, it should be above that one. And we have vertical scale here, measure that height y dash, and horizontally how much that gauge has moved, you measure it x dash. Okay, from the 0. So x is equal to x dash minus x naught, y is equal to y dash minus y naught. That's all the experiment that you have to do. Afterwards, start the stopwatch. For 10 mm rise in this tank due to the orifice water collecting in this tank, how much time it takes, you record it. A typical calculation we are doing, Q actual is equal to H by T, 0.18 into the power of minus T divided by T is 8.1. Next, the Q theoretical A into root of 2GH, A 1.3 into the power of minus 4 into root of 2 into G 9.81, H is 21.2. It is 2.6 into the power of minus 4 meter cube per second. So you will get CD, that is actual divided by theoretical discharge, you will get CD. You can also get CD by using the graphical procedure. Take an ordinary graph sheet, mark 1 unit is equal to 1 into 10 to the power of minus 4 meter cube per second on x-axis and y-axis. 4 trial we did it. One is 25% valve opening, inlet valve opening, another one is 50% inlet valve opening, another one is 75% inlet valve opening, another one is 100% inlet valve opening. Corresponding to that, you will get 4 point best fit curve you plotted. Slope of that curve will give CD as I explained here. AB by BC will give the CD value. So the result is coefficient discharge of orifice meter is 0.83, coefficient of contraction is 0.92, coefficient of velocity is 0.9. So I wanted to explain the line diagram with the existing equipment in government SKJ laboratory. So this is your tank corresponding to this one, overhead tank, and this is the piezometer where the level of water will be recorded, and from here this is orifice stop, piezometer head water will give H once the experiment is started and stand by condition as reached. This is the gauge, this is your horizontal scale and this is your vertical scale. So from here edge to this opening naught is x naught, and from here to here is y naught, and from here if a water ejects up to here means move this gauge here, measure that length, that is y depth y0, the corresponding is x0, and this is the collecting tank, inner dimension L and B, you measure it. You can see here there is a piezometer. For 10 mm rising piezometer, 1 cm rise, how much time it takes, you collect it and enter it in the table, and that's how it works. Okay. Now coming to the multiple choice question, the Orifice are rarely used for determination of discharge. True or false? The answer is false. So the actual discharge through Q act is given AT by H, that is true. Theoretical discharge A into root 2 GH, that is false. Coefficient of discharge CD is theoretical by Q actual, it is false. Coefficient of velocity CV is x square by 2 YH, it is false. Next, the orifice is commonly used to determine discharge, it is answer is A. Actual discharge is AH by T, it is A. Theoretical discharge A into root 2 GH, it is A. Answer is A. Coefficient of discharge CD in orifice is CD is Q actual by Q theoretical, it is A. Coefficient of velocity CV is equal to root of x square divided by 4 YH, it is A. So these are all the list of references we are used, and the actual photographs are taken from Government SKJT in our college, Department of Civil Engineering FM laboratory. I take this opportunity to thank Department of Collegiate Education and Technical Education officers for giving me an opportunity to deliver fluid mechanics and hydraulic machinery laboratory through LMS for all students. Thank you students for attending the class. If you have any doubt, you can ask in the next class.